Okay, so let's talk about, like, if you've been looking at the tests, okay, if you've looked at all of the practice tests, you'll see, you'll start to notice a few patterns. So I'll tell you about, like, the content, okay? The first question is a question about a tangent. You know, it's a nice easy one, and it's a tangent involving some E function, some E to the f of x.
Attention students, could Alex Sticker please go to Osh? Alex Sticker to Osh. Thank you.
So it might be something like, I think this might have been in the 2019 test, I can't remember what I was looking at, but it was like, find a tangent to y equals e to the 3x take 7 at x equals 2. Alright, so that, and in exact form. Alright, so it doesn't want you to round it, just wants you to find it. So that's the first problem, something a bit similar to that. So should we do that, or are people happy with that? I don't want to waste time doing the easy stuff, so people are generally happy with that. Cool. Alright, so that'll be question 1. Question 2 is going to be like what you expect from 3D.1, where we're going to give you some polynomial. Alright, so some function. It's going to be a quartic, and it's like you've seen the standard setup for the past 3 tests where it says find the derivative, draw the sign diagram, hence state intervals where it's increasing and decreasing, hence state coordinates of turning point. And for this question, I'm just going to say, use your calculator to support you. Alright, so differentiate it, use the calculator to draw the sign diagram. You know, it's worth 2 marks. You get 1 mark for the derivative, 1 mark for the sign diagram. You don't get any marks for factorising it and drawing the sign diagram manually. You don't need to do any of that. And so that whole question, you want to make sure you get all of the marks there, because that's sort of probably the easiest question in the test. Alright, get to draw a graph, make sure you draw the graph nicely. I've got some grid there, and so that's what you should set your V window as, get the points all in the right spot. So that's question 2. I think we're pretty happy with those ones. If you're not, have a look at the practice tests and you'll see those questions pop up a lot. So it's about 3D.1 question 4, alright, where it's asking everything. It says find the derivative, when's it increasing and decreasing, when's its turning points, when's it concave up, concaves down, when's its points of inflection. So lots of marks there, got to make sure you get them. And I can't really remember the order from now on, but I will say, you know, there's a rates of change problem. And so it's going to involve some quantity. And so it's going to say, you know, what's the go when time is 1? What's the quantity? What's the quantity when time is 5? And evaluate it. Just use your calculator. I would even just graph the function straight away and g-solve those points. And then it's going to say differentiate the function. What's the go when, what's the rate of change of the quantity when time is 1? What's the rate of change of the quantity when time is 5? So I think we're generally pretty okay with that. Alright, there will be a conjecture. There will be a graphing question. What else?
Optimizing, is there?
There is an optimization as well. Yep. Very good. So, and you know, if we think about the content, we did kinematics. I haven't put a kinematics question in this year. All right. It's assumed knowledge for the exam and that, but I haven't put a kinematics question in the test this year. I'll just have a look. Yep, rates of change, graphing, optimization, conjecture. That's pretty well it. Conjecture and one about stationary points. So, should we go over a few graphing questions then?
Yeah.
Yep, so let's pull some of those out. Did we do all the ones that were in our textbook, in our notes book? Let's see. So, I'm looking at 3D.2. Yeah, we did those, I think. Alright, so can we pull our graphing booklets out then? I'm going to bring it up. Maybe I'll bring it up here on the screen so I can point to it. So, Hayden, have you done all the conjecture problems?
No, I think I'm missing like one or two.
One or two, yep. Josh?
Most of them.
Most of them. Crunchy?
No, not at all.
Has anyone done all of them?
I only need to do
11 and 12, yep. 12, question 12, yep. So, 604 science. Code 3406. And we want graphing relationships between Alright, so I think we've done question 1, that was in our notes book. Or should we do question 1? So on the first page, there's those 4. You did all of those when we did 3D2. So let's have a look at over the page. There's question 1. If anyone says yes, let's do it, I'll do it. But if does anyone want to do question 1, or should we go on to question? Let's look at question 2. Need to finish kinematics first, so we could do this one now, even though I've said there's no kinematics question in the test. So
let's do one that's like the one in the test.
So let's do one that's similar to the one in the test.
Or maybe one that's actually.
Alright, should we do question 3, or do we have a go? Have we all done question 3?
No. Oh, yeah, we can do question 3.
Cool. Alright, so let's go. Consider the function shown below. Its stationary points are at B and D, and the x coordinates are these points. Its inflection points are at A, C, and E, and they've got those x coordinates. Okay, when is the function increasing? Alright, so when is it increasing? When it's got positive slope. So it's going to be between 0 and x is B. Now the reason I haven't included 0 there is because we can see the hollow dot. And the other thing we're told is consider the function. No, we're not really told x is greater than 0, so we would accept that, or we'd accept that. Either of those is fine. All right, so it's increasing there, and it's increasing over here, isn't it? The x is greater than d. Very good. All right, so that's the answer to part A. Part B says, when is f of x decreasing most rapidly? All right, so the function is decreasing over this interval from B to D. And so when is it steepest? All right, well, the steepest slope corresponds with the point of inflection. And we're told the points of inflection are A, C, and E. So the steepest point along here is going to be x is C. So for what values of x is f of x decreasing most rapidly? The answer to part B is x equals C. And now let's draw a graph of f dash of x. So what I like to do is draw a sign diagram first, and that helps me draw a graph, right? So to draw the sign diagram, I'm looking at it, and I can see it's increasing until we get to B, and then it's decreasing until we get to D, and then it's increasing. Now, based off of that, all right, if we're graphing it, there's a temptation to do something like this, isn't there? Okay? But that would only get you 2 out of 3 marks. All right? Because the other thing we need to remember is that points of inflection correspond with turning points. All right? So if we look here, there's a point of inflection at A, which means there needs to be a turning point at A. So there's some sort of local max here. Alright, the local max at x is A. Similarly, there's a point of inflection at x is E. So we're going to have a local max at x is E as well. Alright, and so then all of the points of inflections, A, C, and E, correspond with turning points on the derivative function. Alright? Cool. So that's question 3. Alright, this might be a good question for us to do as well, question 4. So are there any other questions about question 3? So in your notes book, can everyone turn to page, here it is, 40. Page 40. And what that is that's the table that provides a very concise summary of what the function, the first derivative, and the second derivative tell us. Okay? And so that's particularly useful when we have these multiple choice kinds of things. So we've got, consider the graph below. It's drawn from -1 to +1.5, has one stationary point, and then 2 inflection points. Alright, so 1 stationary point and 2 inflection points. Tick the appropriate box to indicate which one of the following statements is true for the interval over which it's valid. So for the whole graph, is it true that f dash of x is greater than 0? So what would that mean? We can look at our table here. If f dash of x is greater than 0, it means it's increasing. Is it increasing over this interval? No. In fact, it's decreasing over this interval. It's decreasing, but it's also horizontal, isn't it? It's horizontal when x is 0. So it's not the first box, it's not the second box, it's not the third box, it's not the fourth box, but it takes... That's not true either. It needs to be the fourth box. Sorry. F dash of x is less than 0 or equal to 0. Alright? Yeah, the reason it's not the last box is because it says it takes positive values. But nowhere along there is the slope positive, right? It's always decreasing or 0. Alright, on to the next one. On the axes below, sketch a graph of the first derivative of this function. Okay, so if that's our function, and we want to sketch a graph of the derivative, we should draw a sign diagram. So the sign diagram is going to look like this. It starts at x is minus 0.874, was it? Minus 1. So it starts at x is minus 1, so maybe I'll put that there. And it's decreasing until we get to 0, and then it's decreasing again until it finishes at 1.5. Alright, so decreasing until we get to 0 where it goes stationary, and then decreasing again. So that's going to be the sign diagram. And then the other thing we're going to look for as well, points of inflection. Points of inflection correspond with turning points, right? And so we have points of inflection at x is 0 and at x is, now we're told at the top, minus positive 0.874. So that's about here somewhere, right? About here, concave down, concave up. So, all right, so if we're going to draw a graph with these properties, here's the y-axis, here's the x-axis. Let's say here's minus 1, and it's below until it gets to 0, and then it's at 0, and then it's still below, right? Okay, so that's sort of the first part of it. But then we're going to reflect about the points of inflection. So we can see points of inflection correspond with turning points. Well, we've got a turning point there. We've got a local max. All right. We need another turning point at x is minus 0.874. So I might chuck positive 0.874. Chuck that in there. So there's a turning point there, and then it finishes there. Okay, so starts here, starts at minus 1. All right, it's below the x-axis because it has a negative slope until we get to 0 where it's horizontal. It still has negative slope, although there's a local minimum there because points of inflection correspond with turning points. All right, cool. And then the next lot of dot points, tick the appropriate box to indicate which of the statements is true. So the second derivative is about when's it concave up, when's it concave down. And so if we're looking at the function, we can see it's concave up, concave down, concave up. So for this one, the last dot point is going to be the true one. It's both concave up, concave down, and 0 because of the inflection points. All right, this is a good one. Clearly mark and label on the graph a point A where the first derivative is 0. All right, so anywhere on the graph where the first derivative is 0, the first derivative is the slope. When's the slope 0? You could put it here. All right, that's where the slope is 0, or you could put it here. Either of those would be appropriate. Clearly mark and label a point on the graph B where the slope is positive. Okay, f dash of x is greater than 0, so it could be anywhere along here and anywhere along here. All right, you put B anywhere there, you get that mark. And then here we've got two things we need to satisfy. Clearly mark and label a point C where f of x is less than 0. Okay, so it's not f dash of x, it's not f dash dash, it's just f of x. So that means the y value is negative. So where the y value is negative and the second derivative is positive. Well, the second derivative is about when's it concave up, concave down. We're talking about when it's concave up because the second derivative is positive. So that would be anywhere along here. It's concave up and the y values are negative. All right, so you put C there, anywhere there, you'll get those marks. All right, this looks like a tricky one. Should we have a go at this one? Consider the function defined for x is greater than or equal to 0. The following information is given. All right. The graph of y whose f of x has a stationary point of inflection. What are the coordinates of the stationary point of inflection? All right, so stationary inflection. I can refer us to our notes, but stationary inflection occurs when the first derivative and the second derivative have the same root. All right, so what we can see from here is that the first derivative is 0 and the second derivative is 0 at x is 3. Okay, so we have a stationary point of inflection at x is 3. All right, so what are the coordinates? X is 3, y is f of 3. We're not given a function, so. Okay, select the correct answer by ticking the appropriate box. For 0 is less than x is less than 3, the shape of the curve is. So between 0 and 3, we have the second derivative is positive. The second derivative is positive, that means concave up, opening upwards. So you check that box. Okay, on the axes below, sketch a curve of the graph of f of x. All right, this is going to be hard. So, let's see what can we. Yeah, we can't really sketch. Let's try sketch sign diagrams for all of them first. Okay, so here's the function. What we can see is when x is 0, it's 2, and then when x is 3, it is -2. So somewhere in there it changes. See how it's faded out? It doesn't really tell us, does it? So it was positive, and then somewhere in here it changes, so it goes below.
Okay, wait, can you explain that again?
Yeah, so if I'm trying to draw the sign diagram here, the function is positive at x is 0, right? It's positive at this point. And then I've got when x is 3, it's negative. So somewhere in between 0 and 3, it transitions, but we're not told where, right? There's some root in here between here's x is 0 and here's x is 3. Somewhere in there is a root, right? And we're not told anything about it beyond 3 either. So that's all we can do for the first one. Let's look at the first derivative. So we don't have any information when x is 0, but we know between 0 and 3, the slope is negative. All right, so that's quite useful. We have negative slope there, and then it's horizontal at that point, and then we have negative slope again. Okay, so that's quite useful for us. That's the first derivative. So what that tells us is it's decreasing, goes horizontal, keeps decreasing. All right, and then for the second derivative, we've got concave up until we get to x is 3, and then concave down. Okay, so let's try bring all of these together. So we're sketching a graph of the original function, and they've given us this plane here. So what's it go from -6 to +6? And we've got 2, 4, 6. All right, so if we're thinking about the original function, right, it's positive. It's, in fact, we're told when x is 0, the y value is 2. All right, so here, the y value is 2. That's the first point. All right. The other thing we're told is when x is 3, y is -2. So that's quite useful as well. So we can plot that, put that point in there, can't we? That's when x is 3, the y value is -2. Okay, so that's just based off of here. I don't know where the root is. There's a root here somewhere, but it's above and then below, and I've just put that point there and that point there. Okay, now it is decreasing, all right? It's decreasing, it's moving down until we get to that point. That makes sense, okay? But the other thing is it's concave up. And so that means I'm not going to sketch it like this because that is concave down. I'm going to sketch it like this. All right, it's concave up, it's opening upwards. It's concave up until we get to that point. And then it transitions to being concave down and still decreasing. Okay, so you notice we're decreasing, but concave down. And that is going to be everything. Yeah. So that's quite a tricky one, isn't it, bringing all that together? All right. Keep going.
Yes,
We're smashing them. All right, on to 7. The sign diagrams below relate to the first derivative and the second derivative of some function. For what values of x is f of x decreasing? So if we look at the sign diagram here, decreasing between -3 and -1, and -1 and -2. That's going to be our answer for part A. That's all okay? Yeah. Part B. For what values of x is the graph concave? Alright, so opening downwards, concave downwards. So that's when the second derivative is negative, it's going to be opening downwards. So x is less than -2, -1 to +1. That's going to be the answers for B. Do you want me to write these down? Or? Yep. So for part A, decreasing from -2 to -1, and -1 to positive. Oh, sorry, that's a 3. And -1 to 2. Increasing. It doesn't ask when it's increasing. Concave down for x is less than -2. And -1 is less than x less than 1. Now, can I just address that as well? Like you're saying, how's he got concave down out of that? This is the old language, okay, concave down. And I did write that in your books. But concave, you just think of a cave, right? It's opening downwards if you're going to walk into the cave. Okay? So they don't tend to use that anymore. They say concave down or concave up. If it just says concave, it's opening down. I won't use that language, neither will Sace. Okay, everyone okay so far? Alright, we've got the function has 3 stationary points, A, B and C. Determine the x-coordinates of points A, B and C and classify them as local max, local min or stationary inflection. Write your answers in the table below. Okay, very good. So, what we can see, if we look at the slope, it's got positive slope, it's horizontal, and then it's negative slope. Okay, so we have a local max at x is -3. Alright, so if A is the first one, x is -3, local max. I'll draw the table up. Alright, then B is at x is -1. And what's going on is it's decreasing, goes horizontal, and then keeps decreasing. Alright, so that tells us it's a stationary inflection, right? Decreasing, horizontal, decreasing. X is -1, stationary inflection. So if you look at when we did 3C, there's 2 ways to tell if something's stationary, and one of them is just off the sine diagram first derivative. Okay, if it looks like this, or like this, that's stationary inflection. Okay, because it continues its descent even though it goes horizontal at that point. Alright, so that's point B, and then for point C here at x is 2, decreasing then increasing, we have a local minimum. Non-stationary point of inflection. You won't tell it from the graph of the first derivative. You have to look at the graph of the second derivative. And it's when the graph of the second derivative changes sign. So there, it changes from negative to positive. And there, because it changes from positive to negative. Sorry, that's a point of inflection. So what you do first is, first you identify that as a point of inflection, and then you check, is it stationary?
So is a point of inflection when it's like when you can see it's -1 from the first and the second derivative, right?
Yes. Yep. So point of inflection occurs when the sine diagram of the second derivative changes sign. Yeah. Yep. Stationary is the special case, and you can tell stationary just from the first derivative.
Yeah.
But non-stationary you can't.
Okay.
Yeah. All right. So let's move on then. So we've got that. We've got the table. We're told the function passes through the point x is -1, y is f of -1, and they've sketched it there for us. draw a graph labeling the stationary points A, B and C as per the table. Alright, so this one's going to be a little bit easier, I think, than the previous one. So, starts here. Alright, that's that first point, -1, f of -1. And let's look at the information that we got from our table. We have a local max at x is -3. Now we're not told the y value at that point, so we'll have to figure that out. Local max at x is -3. It's concave down until we get to x is -2. Alright, so let's maybe, what have we got? We've got stationary inflection there, and we have non-stationary points of inflection at -2 and +1. Alright, so we have a point of inflection here somewhere, and we have a local max here somewhere. I might just put some points on and then adjust the axes accordingly. Although it does say sketch a possible graph. So there's got to be a few, although because they've given us that point, let's see how we go. Let's just wrestle with it. Alright, so we've got, this is a point of inflection, non-stationary point of inflection.
There's another one.
There's another, and this is, the one at 1 is stationary, isn't it? So it goes horizontal at that point. At x is 1. So that's the stationary point of inflection. Sorry, no, that's wrong. That's wrong. -1. This one here is the stationary point of inflection. Alright, so what that means is it's horizontal at that point, but then keeps decreasing, right? Okay, and then we have a normal point of inflection at 1, which is where it's changing shape there. And we have a local min at x is 2. I'm going to scribble all this up here and then talk about why it satisfies what we need. So we've got a local max here, we've got a point of inflection there. Alright, I think that's pretty good. And then here a local min. Local min, point of inflection, stationary point of inflection at x is -1, -2, -3. Okay, so let's see if we've got everything. We've got local max at x is -3. Alright, so that's A. We've got a stationary inflection at x is -1. That's point B. And then we've got a local min at x is +2. That's point C. And then the other thing that they would expect you to include is these points of inflection. So we get them from the graph of the second derivative. Alright, changes sign here from negative to positive, so that's going to be a point of inflection. And then the same here, that's going to be a point of inflection as well. And you can see it changing shape, right? Concave down, and then over this interval, concave up. And then over this interval, concave down. And then over this interval, concave up. Alright, so yeah, that was a little bit trickier than I had anticipated, but we got there. And the other thing to say is, right, it's not clear where these points go, and it's not clear how high up they are. So they could be anywhere on there, right? You're not given the y values, so you wouldn't be expecting, like it just has to have that shape, all right? Doesn't matter the dilation of it. All right, so that's that one. Okay, should we do 8? 8 was in the test, probably last year's test.
No, the year before that.
Sorry?
The year before that.
The year before that, right. This is probably one of the harder ones. Very happy to chat about it. It's a good one to do. Have we had enough? Never? Should we do 8?
Yeah, let's do it.
Alright. Should this be the last one? Yeah, alright. Let's do 8 and we'll finish with 8. Alright, so we've got figure 6 shows the functions here. We've got f and we've got g, 2 functions. The graph of each function has one stationary point located at x is 2. So we can see for f of x it's a local minimum. we can see for g of x, it's a stationary point of inflection, right? Changing shape, increasing, horizontal, then increasing again. Okay. State the nature of the stationary point on the graph for f of x. So the answer for part A is local minimum. F of x has a local minimum. All right. Part B says, figure 7 shows the sign diagram for the second derivative of g of x. All right, so this is telling us where g of x is concave up and concave down. State the nature of the point located at x is 2 on the graph of g of x. So you get 1 mark for saying it's a point of inflection, but it's a stationary point of inflection because we can see it's increasing, goes horizontal, and then keeps increasing. So our answer to part B is stationary point of inflection. And please write stationary point of inflection, but make the shorthand like I have done. All right, on to C. The graph of f of x has 1 point of inflection at x is 5. 1 point of inflection at x is 5. Yep. Okay, that's fine. Determine intervals where f dash of x is increasing. That is very tricky because it's not saying where is f of x increasing, it's saying where is the derivative increasing. All right, so what that means, if we're going to draw the sign diagram, so for part C, it says when is f dash of x increasing? Okay, let's make a relationship here because we're given the sign diagram of g dash of x. Okay. When is f dash of x increasing? So remember, right, if we have the function, the sign diagram of f dash of x tells us when f of x is increasing. Okay, so what that means is the sign diagram of f dash dash of x is going to tell us when f dash of x is increasing. Okay, so let's draw the sign diagram of the second derivative. All right, and so if we're looking at the graph of the second derivative, we can see it's concave up. All right, we can see it's concave up, but we're told there's a point of inflection at x is 5. So because it's concave up, it's going to be positive, and then it's concave down. All right. So the question says, when is f dash of x increasing? Well, the second derivative tells you when f dash of x is increasing between 0 and 5. So our answer to part C. All right, so you have to read that one carefully.
Was that being like that in the test?
It could be. Yeah, this isn't the question I've put in the test. Yeah. Okay, so then we go on. We've got some multiple choice here. Between 0 and 2, one statement is true. Tick the appropriate box. F dash of x is less than g dash of x. So what does that mean? It means the slope of f of x is less than the slope of g of x. This next one says the slopes are equal, and the third one says the slope of f of x is larger than the slope of g of x. Let's have a look at it. Between 0 and 2, g of x has positive slope, f of x has negative slope. So that means the slope of g of x is larger than the slope of f of x. What's the appropriate box does that correspond with? The first one. All right. The slope of f of x is negative. The slope of g of x is positive, so we'll tick the first box. Okay. Still focusing on the same interval between x is 0 and x is 2. One of the statements, so f dash dash of x is less than g dash dash of x. Now it's asking about concavity. All right. And so if we look at both, we can see f of x is concave up, g of x is concave down. All right, so the first, f dash dash of x is positive between 0 and 2, and g dash dash of x is negative. So what's the appropriate box? The third one. That the second derivative of f of x is larger than the second derivative of g of x. Okay. This is tricky. Between 2 and 7, the value of f of x take g of x is increasing. Which statement is true? Alright, let me explain what that means. The value of f of x take g of x is increasing. So over this interval, f of x take g of x, that gap is getting wider and wider and wider. Okay. What does that mean about the slope of the functions? They're both increasing. One of them's increasing faster. F of x is increasing faster because it's getting further away, isn't it? They're not getting closer together. And so that means f dash of x is greater than g dash of x between 2 and 7. Okay, figure 8 shows the graph of f dash of x. Sketch the graph of g dash of x. All right, so we're doing it from 0 to 7. We're doing the graph of g dash of x. Is that what we're asked to graph?
Yeah.
Graph g dash of x. So if we look at the function g of x, right, we can see it's increasing until we get to 2. I'll draw the sign diagram first. It's increasing until we get to 2, then it's increasing again. All right, so what that means, it's going to be above, it's going to touch at x is 2. All right, and you might be tempted there to just draw an arrow saying, yep, and now it just continues. But, all right, where are we told something? We got the sign diagram here of the second derivative.
Point of inflection at x equals 5.
That's for f of x. If we, yeah, you're on the right track though.
So between 0 and 6, so it does, it's not continuous.
Correct, yeah. So at x is 6, all right. This tells us where points of inflection occur. All right, there's a point of inflection at x is 2. That's the stationary point on the original function. And there's a point of inflection at x is 6. So let's look back up at the graph, and you can only just see it. It's not very exaggerated, but you can see concave up, concave down, concave up, and then somewhere in here, x is 6, it changes to be concave down. All right, so you can't see that one from the graph, you can see that from the second derivative. And remember, points of inflection on the function correspond with turning points on the derivative function. So that means we have a turning point on this derivative function at x is 6. All right, so you get the last mark for that part. All right, so that's quite a tricky graphing relationships question. Tricky to see this one. Very good. So yeah, the question